All right, so last time we wrote the finite element equations for poroelasticity, and we skipped the intermediate steps because we've done it enough. I just wrote down the final equations. But of course, if we wouldn't have skipped the steps, the first thing we would have done is develop the weak form, and then we plug in our Galerkin approximation in the weak form. Okay, but if we just were to consider the weak form of poroelasticity, it would be something called a mixed variational problem. And a mixed variational problem would be one that had the form of something like this. Where both A and B are bilinear operators. And these arise a lot in saddle point problems where this A would be some kind of energy and this B would be some kind of constraint. Again, these show up a lot in so-called saddle point problems in the mathematics literature. And so in our problem, our poroelasticity finite element model, the B, this constraint term, is like the Q matrix. Right? So in the first equation, which was, conservation of mass of the skeleton, I'm sorry, conservation of momentum of the skeleton, you had a term that was like this. And in the second equation, the conservation of mass equation, we had a term like that, right? And so since this is the same, we called that the Q matrix, right? And of course, then sort of backing up to our bilinear operator, in the first equation we'd have the del U would be B transpose, which, remember, B transpose is like the gradient of the U-shaped functions. And then the P would be inf-PGE. And then in the second equation, the del P would be NP and then U, or rather U dot, would be B transpose U dot, which again is equal to the gradient of NU dot. So everybody see that? So the Q matrix is like a constraint matrix in the setting of this mixed variational problem. And so one of the most celebrated results in finite element mathematics is the so-called inf-sup condition. You'll see why it's called that in a second. It's also known as the Babushka Brezzi condition. And sometimes also you might see it as the some Polish name, Zinkaja, Babushka Brezzi condition. Okay, so obviously it was named after these guys who, Babushka and Brezzi, I mean, around the same time stated the condition, but stated it a little bit differently, and it was, after some interpretation, you could see that it was the same thing. Yeah.
What is that? U dot equal dt u dot. Yeah.
Well, yeah. I mean, this should be this should be the u as in there, right? I'm just giving you the interpretation, right, of what if we say that our bilinear operator is this, right? Then the interpretation of what u and del p are in the second equation and the first equation are these things coming from this, right? So yeah, so this was these, and I'm going to write it down in a second. I haven't shown you what it is. But these are very celebrated. This is a very celebrated result in finite elements. And does anybody know where this guy works? Babushka? Take a wild guess. He's actually Czech. Take a wild guess where he works. No. You know, right? Yeah. Take a guess.
What school do you go to?
What school do you go to? Right. Yeah. So Ivo Babushka is a professor emeritus, retired professor, and member of the Institute for Computational Engineering Sciences. And he goes to work every day over there in the ISIS building. I occasionally have lunch with him. In March of this year, we're going to have a symposium in honor of his 90th birthday. So he's 90 years old, and he still comes to the office every day, and he's very, very friendly to students. You know, if you're ever working on an interesting problem, he's one of these guys that, if you haven't had an office over there, you know, he's the guy that's always walking down the hall, sticking his head in everybody's door and saying, "What are you working on? What are you working on?" So. I was over there one day talking to him. I mean, he really is, while he's certainly famous for this, he's done a lot of other really great things in the finite element literature and mathematics of finite elements. And I mean, he's one of the greatest living mathematicians and applied mathematicians. And I was over there one day talking to him about some stuff, and we got into a little bit of a disagreement, and we started to write down a free body diagram like you would write in Statics 101. And I just sort of thought to myself, here I am sitting with one of the greatest living mathematicians drawing a free body diagram, because it was very elementary. But anyway,
who won?
I think we had the end to agree to disagree in the end. Yeah. So what the and again, I'm not going to derive the inf-sup condition. I'm just going to write it down. But basically what it says is that if there's some positive constant gamma, if you can find a positive constant gamma, it's called the inf-sup parameter, or inf-sup constant, such that the infimum of P, I have to write a little bigger, P not equal to 0 of the supremum of U not equal to 0, such that the norm of the bilinear operator, the constraint term, is something like that. Okay. So basically what this is saying is if you can prove that this is greater than some positive constant, right, you actually can prove this is a sufficient condition for the solvability and uniqueness of that system of equations up there. Okay? So proving inf-sup is sufficient for solvability and uniqueness. Or another word to say that is what? If a system is solvable and unique, what is it? It's well posed, right? So this is a condition on the well posedness of that. Because just because we can derive a system of equations from a variational principle doesn't mean it's well posed, right? Necessarily. And we could go on computing solutions to that. But unless we have the mathematical theory that says it's unique, how do we know that that's the answer, right? So does everybody know what the inf and sup are? Right. So it's sort of like max and min. Sup is like max, inf is like min, except max and mins have to be bounded, right? These infs and sups always exist because they can be infinity or minus infinity. But if they actually exist in a finite sense, then they
don't necessarily have to be
attained. Attained. Yeah. If they can be attained, then these are just max and min. Okay, so